So in this video, we are going to discuss the leave one out or leave one out validation approach. Leave one out validation approach. So LOOCV. This is almost similar to our validation set approach, but then it tries to address the two drawbacks of that validation set approach. How does it do this? The similarity is we are going to split our data into two sections, right? Into two parts. That is the similarity. But then the two parts that we are going to do, it's going to be something like this. This is our full data set, right? And like previously we had 1, 2, 3, all the way up to n. So the way it's going to split this, it is going to say, it's going to take one data point. It's going to take one data point like that, one observation, and put that aside, and then the rest here will be the second set. This will be the second set. This will be the second set. And this second set here for everything else will be the training set. And that one that we took out will be the validation set. That will make the validation set. So essentially what we're doing is it's going to take a single observation, let's say x1 and y1. That's a single observation, right? And this is going to be our validation set. And then the rest, x2, y2, x3, y3, all the way up to xn, yn. This will form our training set, right? So our training set will be like this. Let's just put some mathematical notation here, like a set notation. The set notation like this. Perfect. So now, the statistical learning method, if you can count how many they are, these are n-1 observations. So the statistical learning method is going to be trained on n-1 observations, on n-1 observations, and a prediction y1 is going to be made for the observation that is in the validation set. So we're going to train it on here, and then after we've trained it on these n-1 observations, we're going to do just like we did in validation set, we're going to use the statistical learning method to do a prediction on this one that we left out. We're going to come up with a predicted y1, right? Because when we put the x1 inside our statistical learning method, we are going to come up with a predicted value. The difference between y1 and my y predicted, this is going to be our error, right? This is going to be our error. And that error is the validation set error. We're going to call that our test error. But what we call, let's use regression as an example. Cool. We are going to call that our MSE1. That is definitely the MSE error for the first observation, right? We do not stop there. We're going to say, cool, let's now take point number 2 or observation number 2 and put that in the validation set. And now in the training set, it's going to be composed of point number 1, 3, 4, going all the way up to n. So let's write the steps there. Step 1. So this is going to be our validation set. Let me just write the validation set here. The validation set column, and this is going to be our training set column. Training set column, right? Training set. And we are going to write our error, the error that is going to be there, right? So that is step 1. What is going to be in our validation set? It's going to be the first observation. And in our training set, it starts from the second observation all the way up to the last observation. That's what we're going to do, right? And then when we do our training, we're going to predict the model that we come up with. We're going to apply it to our validation set, and we come up with our y1 predicted. And the difference between the two here is going to be our MSE1. If we are talking about regression is easier for us to explain, but this applies to any statistical model. Just the error, the way you calculate your error is different. If it's classification, you just count how many, if it has been misclassified and stuff like that. But for our case, this is going to be our MSE1. And we'd repeat this process, step number 2, but we leave out what? We leave 1 out. Which one are we leaving out? We are leaving the second observation. When you leave the second observation, our training set is going to be include that x1, y1, and then it's going to skip x2 because x2 has been put into the validation set, and it's going to say x3, y3, all the way up to xn, yn. We train it on this. We train it on this set here, and then we predict for x2. We put x2 into the model, and it's going to predict y2 like that. It's going to come up with the y2 prediction like that, and we calculate our MSE2. We do step number 3. Step number 3 involves us leaving out observation number 3. So in our in our training set, we have x1, y1, x2, y2. We skip x3 because it's now in our validation set. We go to x4, y4, all the way up to xn, yn. And then after training it, we use that model to predict for x3. We come up with y3 predicted like this. We calculate the MSE. We have MSE3. All the way up to step n. Step n means we are going to leave 1 out. Which one are we leaving? The xn, yn observation. The last observation. And means our training set is going to have our x1, y1, x2, y2, all the way up to xn-1, yn-1, or the one just before the last observation. We train our model here, and we predict for the last observation for our xn, and we come up with a yn predictor. We calculate the MSE, we are going to have MSEN. Right? We're going to have MSEN. Cool. I think that makes sense, right? That makes sense. So now that we have calculated our MSEs, we have n MSEs, and we have repeated, because we have repeated this for all n observations. When we have done that, we are going to calculate the LOCCV, or the leave one out cross validation error, and it's going to be given by this. It's going to be, let me just say, I can write it as LOCV is equal to 1 over n summation I equal to 1 up to n of my MSEI. I think this makes sense. This makes sense, right? Because basically we have just added all the MSEs and divided by n. So we just calculate the mean. We calculate the mean MSE. We calculate the mean MSE. That's what we're doing here. This is the mean. We just added up all of them. The summation sign is saying add up all the MSEs from the first one to the nth one and divide by n, the number of MSEs they are. We have n MSEs. So this is just the mean. This is just the mean, right? And that mean will be our estimate for the test error. That becomes our estimate for the test error using LOCV. Yeah, that's going to be our test error estimate, right? So this has advantages that we can already pick up from the validation set. It has less bias. So this is the advantage. It has less bias, right? Because the model is repeatedly fit using sets containing n-1 observation, right? n-1 observations, which is sort of almost the same as the whole set itself. Here, basically, we're fitting with n-1 observations. -1. Imagine if we had 1,000 observations, which means at each stage we're fitting the model with 999 observations. So it has less bias compared to the other one. The validation set was splitting into 2. Validation set would have trained on 500. So depending on how you select your 500, you might introduce a lot of bias. But here we are training it on almost the whole data set. So it reduces the bias because we are training it on almost everything that we have currently. So it has less bias. Number 2, it tends not to overestimate the test error as much as the not much overestimation of test error, because of this same reasoning, because there's less bias now. So we are much closer to the test error than we were previously, right? And then 3, performing this always yields the same results because there's no randomness. So consistent results, because there's no randomness in training validation set choices, unlike in that validation set approach. Because the validation set approach, if you're saying choose 500 out of those 1000, there are many 500 training, there are many training sets you can pick with 500 each. There are many of them, right? So yeah, there are many of them. But this one here, because we're training on almost similar looking training sets, as you can see, 999. If you take one out, what is the difference between when you take the third one and when you take the, let's say, the 500th one? The training data set that you're using there, it's almost 99% the same. So the results are going to be consistent each time you run it. But some people can already pick up one disadvantage. High five yourself if you picked up one disadvantage that's going to be there. The biggest disadvantage is this is going to be computationally expensive. It's going to be computationally expensive because you have to run the model n times. You have to create n times or n MSCs. You have to create n MSCs. You have to run this. You have to fit this model n times. So it's going to be computationally expensive. If you have 1 million observations, it means a million. You are going to fit the model 1 million times for you to come up with 1 million MSCs. And that's going to be very computationally expensive, especially if you have a large data set and stuff like that. It's going to be very computationally expensive. So this disadvantage, it's going to be addressed by the next method now. The next method, called k-fold cross-validation, is going to try and address this disadvantage of being computationally expensive. These are the parts we are happy because we have improved on the validation set, but we are not happy about this one. And we are going to see if k-fold cross-validation can make us happy on this one. So stay tuned for that video.